If we take two radii and put them together, they actually sweep out what's called a sector. If you take a look at this circle here, circle centered at A, then what you see here, we actually have two sectors. We've got this purple sector, which is this region right here, and we've got this teal sector, which is this other region here. And so it turns out that we can actually study these sectors, which you can see are just part of the entire circle. So for example, if you want to find the area of a sector, obviously it's going to be some appropriate fraction of the area of the circle. Now the area of the circle, of course, we know is pi r squared. So how do we figure out the appropriate fraction? Well, that's given by this neat formula. Pi r squared, that gives the area of the whole circle, and this is the fraction that's required, which is, we know that the total angle around is 360, and so all we need to know is the measure, either the measure of the central angle or equivalently the measure of the arc, and then we can actually figure out what the area is, because that will give us the fraction of the area that we want. So for example, here, suppose that we want to find the purple area of the area of the purple sector. So that would be the area of the purple sector, DAE. How would we do that? Well, we would just find out what fraction of the area we should consider. It's not a really big deal. So if you want to find the area of sector DAE purple, that would equal pi r squared. And so here we see that r is 5, so that's going to be 25. And then I'm going to multiply that by the appropriate fraction. Well, I'm given that the measure of this arc, the measure of this arc is 150 degrees, so I put that over 360 degrees. And so what do I get? I get, in fact, let me put this piece of paper here so you can see this a little bit better. And so what I see here is, well, you can actually reduce this down a little bit. I could simplify that a little teeny bit. Pi times 25, I can put 15 over 36. And if you actually compute this on a calculator, you'd see 32.7. And what are the units? Well, this represents area, so it's inches, but it's inches squared. Inches squared. So you can see how you can use this formula, which I think makes a lot of sense in finding the area of sectors. It's literally the area of the circle multiplied by the appropriate fraction of the circle that you actually are. No big deal. Okay, now I want us to look at objects that are formed by truncations of a circle that are called segments. Now, what's a segment? Well, a segment is what you get if you take a chord and draw a chord on a circle, and look at the little piece, the little crescent moon kind of piece you get by looking at the shape between the chord and the arc of the circle. In this case, it's marked in red. This is an example of a segment. Now, it's easy to get confused between a segment and a sector. So I'm going to actually share with you something that I learned a long, long time ago when I was actually in high school and I was taking geometry. My geometry teacher told a great way of remembering the difference between a segment and a sector. And you know what? It stayed with me for like a million years. Okay, I'm not a million years old, but pretty close. And here's what she said. She said, sector, it has an O in it, sector, and usually we think of the center of a circle as being sometimes using the letter O. So sector, so that means that we actually go to the center. So that's a sector. And a segment, since it has no O in it, that doesn't include the center, the origin, and so it's just that little crescent piece. And you know what? It stayed with me ever since. So maybe if you like that, you can remember it that way too. Anyway, suppose that we want to actually find the area of a segment. Well, what's the formula for it? I guess we can write one down, but it's easier to think through it. It turns out that if you think about it, this little crescent red is made up of two pieces. We take the area of the sector, which we know how to find, here's the formula for it, and then just subtract off this little piece. But that little piece is just a triangle. And we know the area of a triangle. So in fact, all we have to do to find the area of a segment is to find the area of the analogous sector and subtract off the appropriate triangle. Let's try an example and see all this stuff in action. So here I'm given a circle. I'm told this is 60 degrees, this measure of the central angle. The radius is 18. And my mission is to find the area of the red segment. And the way I'm going to do that is first find the area of the sector and then subtract off the area of the yellow triangle. Now, the area of the area of the sector is easy. So the sector BAC area is going to be easy. I just use the formula. So I see pi, now r squared is going to be 18 squared, times the appropriate ratio, which is going to be 60 degrees over 360. So that's 1/6. And so I see that this is going to be equal to 54 pi when we simplify that down. Okay, great. But now what I've got to do is I've got to now subtract off the area of that yellow triangle. Aha. Now this is going to be a little bit tricky, so let's think through this. First of all, notice that this is a radius and this is a radius, so they're both 18, which makes this triangle actually an isosceles triangle. So therefore, these two angles must be equal. And if they must be equal, then I know something. In particular, I know that since this is 60, what's left here is 120. Therefore, everything is 60. This is an equiangular triangle, which we know, therefore, is an equilateral triangle. So in fact, every single side has length 18. Now, this is a very special triangle, and we can actually analyze it to find its area. If I drop a perpendicular, since this is 18, then I know that this is a perpendicular bisector, and this is a 30-degree angle. And this here is 9. And therefore, we can either notice that we have a 30, 60, 90 right triangle, or we could actually use Pythagorean theorem. But any way you want, we can compute that this altitude, this height, is 9 square root of 3. And I'll let you do that any way you want. You might remember that, or you might actually just want to use the Pythagorean theorem and generate that yourself. Anyway, the point is we can now compute the area. It's going to be 1/2 base times height. So that's going to be what in this case? That's going to be 1/2 the base, which is 18, times the height, which is 9 square root of 3. Okay? And so, what do I want to do? Well, I take this answer, that's the whole sector, and subtract off the area. So I subtract, and so what do I see? I see 54 pi minus, and this works out to be simply 81. We can see that because the 2 and the 18, when I divide, I get a 9. 9 times 9 is 81. Square root of 3. That's the exact answer. If you want an approximate answer, you can put it in the calculator and see 29.35 inches squared. And so there you can see how to find the area of a segment by taking the area of the analogous sector and subtracting off the area of the triangle.